All right. I'm going to do the last part. If you are following my videos, I posted one that solved complex equations, and I was taking quite a number of long ways to get to the answer by using the multiplicative inverses, everything mixing the division algorithm and the Bezold identity. So let's do the last part that looks at how best can we also approach this type of equations, complex equations. We are going to look at what we call the Fermat theorem. He was a great mathematician, a lawyer. I think he actually was it in the 14th century. He did quite a number of interesting theorems, looking mainly at prime numbers. You understand that I would say prime numbers are the queen mother of mathematics. Understanding prime numbers simply means you understand everything about numbers. And you understand everything about mathematics because everything is tied to prime numbers. So Fermat theorem states that if P is a prime number and A is any number not divisible by P, then A to the power of P minus 1 is congruent to 1. So, and then A to the power of P is congruent to A in mod P. It might happen that you get to a point where you don't have these conditions. That usually happens. For example, the example I worked, at some point in time looked like this: 75x is congruent to 12 in mod 237. So you find out that this divisor is not a prime number, or is it? Yeah, it is. However, the GCD between 75 and 237 is not 1. So we actually, in order for us to have these conditions, we actually need to reduce this by dividing by a number that, in this case, I think if you divide everything by 3, we're going to be left with 25x is congruent to 4 in mod 79. I think it's safe for me to conclude that this is a prime number. Then we can now solve it by doing this instead of going through the Bezold algorithm to find the multiplicative inverse of 25, which I believe is 19 in mod 979. This can be summarized in using this of theorem, which is the Fermat theorem. That's a very, very interesting theorem in mathematics. All right. So let us look at what exactly does it help us in solving these equations. So we are saying, let's look at the next example. So we are saying a bit of some technical glitches here. So we are saying, let us find the remainder if you divide such a big number as 3 to the power of 202 in mod 11. So what we can look at is the divisor itself, which I can call P, is 11, is a prime number. So because of that, the Fermat theorem says if P is a prime number and A is just any integer, then we can say A to the power of P is congruent to A under mod P. But in the case that A is not divisible by P, if that is the case that A is not divisible by P, then we can say that A to the power of P minus 1 is congruent to 1 under mod P. So in this case, is A divisible by P? Obviously, we can see that 3 does not divide 11, so we are going to use this part. So that means we are going to have 3 to the power of 10 being congruent to 1 in mod 11. So it satisfies that part. That's the part we are interested with. Right? Seems like it's been done here. I'm going to remove it so that I can re-explain it. So as a result, we are saying we know already what is 3 to the power of 10. It is equivalent to 1. But what we want is we want to rise to 3 is to the power of 202. So it is much easier now to say 3 to the power of 10 times 20 is congruent to 1 to the power of 20 under mod 11. Because we know that 1 to the power of 20 is still 1. And this part here is just 3 to the power of 200, which is congruent to 1 under mod 11. Happy? Now, if we know this, it also means we can extend it to 3 because our question is 3 to the power of 202. So what we're going to do here is to raise this to 302 by simply saying 3 to the power of 2 times 3 to the power of 200, which we know is congruent to 1, but it's also congruent. Yeah. Which is under mod 11. So that simplifies everything there. And this left-hand side is definitely 32002, which is congruent to 9 under mod 11. And since 9 is less than 11, so we can say whenever we divide 302, 3 to the power of 202, the remainder is 9. So our remainder here, the remainder is 9, using the Fermat theorem. So it's a case of seeing the conditions that are there, and then you use them to justify your answer. All right, next example. You went on to solve this type of equations. It says again, if P is a prime number and P does not divide A, it goes on to tell you that the GCD between A and P is 1. So if we've got an equation of this form, it means it is exactly one solution in the set of the residues under modulo P. That's basically what it means. It has got exactly one solution. And because we are saying because the GCD between A and P is 1, it tells us that we cannot divide anything with A and P. There's nothing that is common. And as a result, if A does not divide P again, we rather just find the number which we call the multiplicative inverse of A. But however, because the conditions have been satisfied already, Fermat theorem suggests that we no longer need to do the Bezold algorithm. We just need to know that the multiplicative inverse is simply A to the power of P minus 2. That's all. That's basically the idea why it is important. A good example is to look at this equation. If you look at this equation, first of all, if I'm to state the conditions, the GCD between 7 and 11 is 1. Clear. And there is nothing common between 7 and 10 as well. So we can't do anything to find x. So we need to find the inverse of x of 7 here. But do we really need to go through the process of finding x, the multiplicative inverse of 7, by doing the Bezold algorithm? No, we are just going to use the Fermat theorem that says the inverse is A P minus 2. In this case, it is 7. P is 11, so it's 7 to the power of 9. That's our inverse. So what are we going to do? So this implies that we are going to multiply 7 to the power of 9 times 7x is congruent to 7 to the power of 9 times 10 under mod 11. So these two here cancel each other to give us x is congruent to 7 to the power of 9, 7 to the power of 9 times 10 under mod 11. This is also a big number, 7, but we can reduce it as well. We can reduce it because we know that 7 to the power of 9 is not that big, but we can say, what is 7 to the power of 3? 7 to the power of 2 is 49. That's quite a small number to deal with, but let me say, what is 49 times 7? That's 343. And if we divide 11, so we know what it means is here we're saying 7 to the power of 3, which is equal to 343. How many 11s are in there? I think it is going to be congruent to 2 mod 11. Yes, that's it. So that's the case. 7 to the power of 3 is the same as 2 mod 11. So if we want 7 to the power of 9, we're going to have to do to the power of 3, which is congruent to 2 to the power of 3 in also mod 11. So that tells us that this is congruent to 8 in mod 11. So taking it further to the equation that we are here, our equation said x is congruent to 7 to the power of 9 times 10 in mod 11. And we've just established that this is equivalent to 8. So this is going to be 8 times 10 mod 11, which is also 80. And if we take away 11s in 80, we are going to be left with x is congruent to 3 under mod 11. So the Fermat theorem presents us with an opportunity to solve these equations in a very, 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 very short way, rather than dwelling with the method algorithm. All right. The next question, which is the last of my lecture, is find the remainder when 2 to the power of 1,000 is divided by 13. So that's very interesting. So if we divide with 13, let me just remove this. First of all, let us look at the conditions that are placed in this algorithm. So the Fermat theorem tells us, can we look at the divisor? Is it a prime number? Yes, it is a prime number. Next, does 2 divide 13? 2 does, okay, let me just write them down. 2 does not divide 13. And again, 13 is prime. So as a result, it tells us that A, the theorem says, in that case, A to the power of P minus 1 is congruent to 1. So what it tells us that is 2 to the power of 12 is congruent to 1 in mod 13. That's what this statement tells us. And we want to get to 1,000. You might think of a number that we need to multiply with here to get to 1,000 from a power of 12. From a power of 12, maybe this is a time to use calculator. I think you get probably 2,996. 2 to the power of 12 to the power of 83 is congruent to 1 to the power of 83 under mod 13. And this is equivalent to saying 2 to the power of 996, which is congruent to 1 under mod 13. So we have reduced it by simply applying the theorem. That's all, instead of going all through that long method. So now we are going to say, since we've got 2 to the power of 996, what we are interested in is 2 to the power of 1,000. So we just need 4. And we're going to put 4 both sides, 2 to the power of 4 both sides. And this is reduced. And we know this is 2 to the power of 1,000, and it must be congruent to 2 to the power of 4, which I believe is 16, under mod 13. However, 16 is greater than 13, so we apply again the residue module. The residues is take away 13 here, we are going to have 3. Number 13. That's our answer. Right. That is it for me.